All right, so going back to the example that we were working on before, the examples, x, oh, sorry, I misread it. This is x cubed. I kind of like a payoff to that, so let's make it x squared. Because we just did two examples like that. I want to show you how to actually get to the exact value. So, first thing I need to do is figure out my delta x. All right. B minus a over n. B is 2, a is 0, n is n, so 2 over n. All right. Then I want to come up with a general expression that represents the position along the x-axis. For that, we use the expression a plus I delta x. If you're starting off with a, and you're moving I movements in terms of delta x along the x-axis, that'll get you to any position of an important point along the rectangle. Or, I'm sorry, along the region corresponding to a rectangle. All right. So, a is 0. I we want to keep variable because we want it to be any I. I want this to allow for me to be at any position under the curve. Delta x is 2 over n. All right, next up is to find or to evaluate the function. And I might as well simplify that. 2i over n. Evaluate the function, and it's y equals x squared, so square this. All right, so I'm just squaring my a plus I delta x. All right. Then I have to multiply that by delta x. And that'll give me the area of any arbitrary rectangle under the curve. Go back to red. So I have 8i squared over n cubed. Right. So then, really, if you think about this part of it represents the height of any rectangle. The delta x represents the length of the base of any rectangle. Multiply the two together, you have now an expression that represents the area of any arbitrary rectangle under this curve. If I know which rectangle I'm looking for, the 10th, the 20th, the 300th, whatever, that's the I value, that's the position. And if I know how many subintervals there are in total, I would now know the area of a single rectangle. But the thing is, I want to have all of them. I want to add them all together over the interval. So what I want to do is find the sum of all that. All right, so then the question becomes from what to what? So we need an index, and this goes back to last night's homework. We need an index, a starting point. I equals 1. We want to go from 1 to n. All right, I want to start with the first rectangle and go to the nth rectangle. Now that's a bit of a conceptual piece because the left rectangular approximation starts with 0 and goes to n minus 1. If you come in, this is the part that I skipped, if you come in from the right, you would start with an I value of 1 and end up with n. Right? But as you apply limits, they both end up giving you the same amount. They give you the same quantity. So it actually doesn't matter which direction you come from. as long as you're applying a limit. Right? So if you're doing it numerically, you just follow whatever the instructions are. But if you're doing it for the purposes of applying a limit later on, then it really doesn't matter which direction you're coming from. The reason I chose I equals 1 to n is because that corresponds with some of the rules that were on the homework from last night, which we'll get to in a second. All right. Now, this summation is in terms of I. So that means that the only relevant variable in this summation is I. What that tells me is that everything else can come out. They don't need to be there. So I could rewrite this as 8 over n cubed times the sum from I equals 1 to n of I squared. If you're going to get jammed up, this is where it's going to happen, because everything else is procedural. You just study the process. This is the rule. All right, I'll show you where it is. In theory, different day maybe. All right, so first thing I'd want to figure out is delta x. So b minus a over n. All right, so the a value is 0, the b value would be 1. So 1 minus 0 over n. So that's a nice clean 1 over n. If you use an a value of -1, then you'd have 2 over n. Not terrible, but it's in the next step that things will be nicer using this approach. A plus I delta x is 0 plus I times 1 over n. So just I over n. All right. Next step in the process is to evaluate that function for a plus I delta x. Now the original function is 1 minus x squared. So 1 minus that I over n quantity squared. All right. So this is where we're saving ourselves time and energy, right? Because we're looking at 1 minus I squared over n squared, which is not terrible, but it's not bad at all, actually. The reality is, though, that it could have been much worse. Right? So if you had an a plus I delta x that started with a -1, you would be taking -1 plus 2I over n and squaring that. All right? So you'd have a binomial that you'd have to square out and then clean up. That's not fun. All right? So then what we're going to do is multiply this by delta x. That's going to give us the area of each of the rectangles that would exist underneath the curve on the interval. So every one of these, I'm just going to draw them as thin lines. Every one of these represents a very skinny rectangle. The area of each one of those is determined by this, this product. All right, so I'm taking my 1 minus I squared over n squared and multiplying it by the 1 over n.
Is it I over n or 1 over n?
It's by delta x, so it would be the 1 over n. All right, so we have to distribute it through. We'll get 1 over n minus I squared over n cubed. All right, we could bring it together if we want, but really it's not necessary because the next step in the process involves the summation. All right. And again, all we really need from this is the rules that we talked about yesterday. right? So notice how a lot of this is irrelevant to the summation. Right? The index is what drives the meaningful variable within the summation. Right? So in this case, because it's an I, the only variable I care about is I, which means everything else can be pulled out. Right? So that's important because after I perform the next step, it's going to clean up kind of nicely. Right? Summation rules, they kind of go hand in hand with limit rules, derivative, antiderivative rules, and that is if you have a sum, you can break up the summation by the sum or difference. All right, so it's like a sum of a sum, which is a really weird thing to think about. But I could write this as the sum from I equals 1 to n of 1 over n minus the sum from I equals 1 to n of I squared over n cubed.
What's the bottom part mean?
The I equals 1?
Yeah.
That's your starting value if you were to expand the sum. So I would plug in a 1, well in this one I plug in a 1 for I, and then I plug in a 2 for I, and then 3, and then a 4 simplify, and then add it all up. So in each case, there's elements that can be pulled out of the summation. So for the first sum, I have a 1 over n that can come out. Doesn't have an I in it. And for the second one, I have a 1 over n cubed that can come out. All right, so we have rules for both of these. One of which we talked about yesterday, but the other is in the same chart. All right, so the two rules that are relevant would be the first one, because the C represents a constant, and the third one. All right, so if you have a summation involving just a constant, all you're going to do is multiply the constant by the upper bound, right? And that'll give you the sum, right? The other one we talked about yesterday, so that's not new information, right? So for this problem, we're looking at a result of, again, if we're just taking the constant multiplying it by the upper bound, we're just talking about n as the result. So 1 over n times n minus 1 over n cubed times n plus 1 times 2n plus 1 all over 6. So then we just have to clean this up. All right. Now, the temptation might be to cancel the n's. And to some extent, you want to do that, like this n with this, to give you an n squared. But for the first one, since we have to get a common denominator anyway, I'm going to leave it as n over n for the moment. And the other one I'll distribute out, 2n squared plus 3n plus 1 all over 6, n squared. And then I'll just, for the first fraction, I'll multiply top and bottom by n, so it'll make it n squared over n squared. All right, you can find the limits separately, but it's, for me, I find it more convenient to just put it all together. I don't know, maybe it's not convenient. It can go either way. You know what? Maybe I'll do it the other way. Just leave it at a 1. Yeah, because then what we're going to do, because what we need to find is the limit as n approaches infinity. So what we're going to do is apply a limit as n approaches infinity to this whole shebang. All right. So that's going to give me the limit as n approaches infinity of 1 minus the limit as n approaches infinity of this whole thing. Limit of a constant is equal to a constant. Two over 6, which would be what? 1/3. And so as a result, we would get 2/3. Now, is that our final answer?
No.
No, because I asked the question. So it can't be.
Meters squared.
Not multiplied by 2, yeah. It was only half of the area that we needed. So 4/3. Yeah. This is equivalent to the integral going from -1 to 1 of, what was it, 1 minus x squared dx. All right, this is the same thing as that. All right, and I'll show you in the next page, I think, or pages, the transition from this way of working through it to that, or at least the symbolic transition.